CMOS on the base of N substrate. But we can construct the CMOS on the base of P substrate, make N well, and most of the devices consist of N modes and just local P modes. Okay, just the other way around. Actually, that configuration is mostly used for the current CMOS device, because we have talked about this last time, but if you make a let's see, you set the P substrate and then build a NMOS, N plus and N plus, and then N well by ion implantation, and then form a PMOS, P plus, P plus. This is the just reverse of the CMOS structure shown in this slide. This is the field oxide, but currently most of the modern CMOS has a structure like this instead of this N substrate thing, because in this way most of the MOS transistor will consist of this NMOS, and then just on the spot necessary for the CMOS, we can build the PMOS. And the NMOS is much faster than the PMOS. So we want construct most of the transistors on the basis of NMOS by using the P substrate. Okay? But in this lecture note, we have a structure like this, and then we make a discussion on the basis of this N substrate CMOS structures. All right? You can make a same argument for the P substrate CMOS structures, exactly the same way that we're going to develop in this class. Okay. Excuse me. I think I'm losing my voice because of the dust problem these days. I think it's basically come from China. Well, if you look into the CMOS structures, you can find the two bipolar connected to each other, and one is this is the PMOS, and this is the MOS, and this is just a contact, okay, to the substrate. This is a contact to the well, P well, and this is a contact to the P substrate, N substrate, the whole wafer. Okay, so when you make an input, you're going to make an input on this, and then you're going to take out the voltage here and the P plus there. So as a whole, the current can pass through this, and then if you look into the current, of course this current we do not want, but it can have this current flow, and then we're going to discuss about that current flow. But if there is a current which is going from this VDD part to the VSS part in this inverter, in the CMOS, now you can think a P plus and N minus substrate, and then P minus bipolar, one bipolar here, and then another bipolar, which is N plus, which is a source of this N modes, and then P well, P minus, and then N minus substrate, which is a vertical bipolar transistor. So you have a lateral bipolar transistors and vertical bipolar transistors, and then they are connected in this fashion, if there is a current. And we're going to discuss about how can this current can be triggered. We do not want, but it's going to be triggered in some operation conditions of this inverter. Okay, and you may notice the resistance here. Of course, this, if you have a big resistance at this part, then the current flow will be minimized, will be reduced. And another resistance here, if this resistance is large, then the current path is going to be blocked somehow. Okay? So this current resistance is related to the N substrate, and this resistance is related to the P well. And one example is if you want to miniaturize your transistors, okay, to have a high level integration, then you have seen in the scaling law, you have to increase the N substrate doping level in order to reduce the size of the transistors. Okay, and then that is related to the resistance here, and this resistance is, if the resistance becomes low, or to make the transistors small, then we are going to have more chance to latch up to occur, Okay, so miniaturization basically is not good to prevent the latch up, or rather it enhances the chance to have a latch up in the CMOS structures. And this current is not going to do anything for the device operation, but if you have a current which is from there's a drain and that source there, then that current is going to be enormous, because this is the bipolar is triggered. And then because of the gain of this bipolars, you can immediately see that you're going to have a very large current, and that the large current is going to burn out this transistor. And think you are going to have hundreds of thousands of transistors collected in a small space, and each one has a joule heating because of this high current. Then the whole thing is locally melted down, and the device is going to be destroyed. That is the problem. The current itself is not a problem at all. And that is very crucial in a sense that once it happens, the burning happens, it cannot be restored. The whole device is going to be ruined, okay, because of because the chip is destroyed. So that's a very big problem. You cannot neglect this latch up things to happen. Okay, that is very much related to the reliability. So this is a very important topic that we have to discuss, and this is a basic. We can think of loop, sort of, corresponding to that latch-up circuit. Okay, this RP is the resistance at as we have seen in the RP is the resistance here, this part, okay? Rn is the resistance here, and then this Rp is connected to this bipolar, and we call this lateral bipolar, and then this Rn is connected to this bipolar, we're going to call vertical bipolar, okay? And then let me see, where is the loop? And according to, wait a minute, why I cannot find the, let me see, let me just for a minute. Okay, this is the criterion for the latch up to occur. The beta NPN, which is a vertical bipolar, should be if it is larger than these values. This has been developed by the PhD student in Stanford University in the United States. And he showed, he derived this criterion. And then according to this criterion, the vertical bipolar transistor beta gain, if the gain of a vertical bipolar transistor is larger than these values, and this value consists of PNP, that is the lateral bipolar transistor gain, and RP, the resistance that I just talked about, and Rn here. So if this criterion is met by some operation conditions, then the latch up is going to happen. And this is the typical numbers for the operation, and then it can be seen that it is not difficult to satisfy this criterion. So we had to do something about this. We have to do something on the structure not to meet this criterion. So that's what we're going to talk about. Intuitively, we can have some few things to prevent. How we can prevent the latch up, and before to find out the structures to prevent the latch up, first we want to see how can latch up can happen. The first thing is over voltage on the VDD input. Sorry. And then this avalanche process, we're going to give you the hose generation at this end, and then this whole generated hose is going to be collected to the P-well, which means this hose is going to be the base current of the lateral bipolar transistors, and it is going to trigger it to forward bias the lateral bipolar transistors. And enormous current can happen by this triggering process, okay? And the other thing is a voltage transient. If you switching the device many times and during the switching, the depletion layer is going to be widened and shrink, depending on the voltage that you apply, okay? And then that variation change will give you the generation of the current which can be collected to the lateral base transistors as well. So this is inevitable. you have to do some switching operation, and then during that switching, the voltage will give you the new current, which is going to be the base current of the lateral bipolar transistors. And input protection overdrive. It is this is the input part of the network, okay? And then you have a P plus N minus diode here, and then you have a N plus and P minus diode here. You have two diodes, and then somehow if you have a over voltage on this input, then this one of the diodes is going to be triggered to have a large current. Okay, so these two diode, along with a current limiting resistor of the input protection network, will give you the latch up a new current to turn on the transistors, bipolar transistors. So we have to think that latch up can happen in real practice, and then the criterion which has been derived by the Stanford University PhD in Stanford University, if you believe this criterion, then it is the current CMOS structure as it is very vulnerable to the latch up. Okay, so what we have to do is, it says scaling or the increase to lateral and vertical bipolar transistors gain, because the base width becomes narrow, which is going to enhance the gain of the bipolar transistors. So the scaling is not good as far as the latch up is concerned. And RP and Rn, the resistance of related to the input and output part, are not going to be changed much, because the small geometry lowers the substrate doping, and so the device becomes vulnerable for latch up. Okay, there are several ways to minimize the latch up occurrence, but entire protection is not possible. So I use the words minimize. But if once it happens, then the whole thing is going to be destroyed. So we have to do something about it. You have to do it. You have to. This is not kind of thing that you can be careful about. You have to do. You have to make a protection not to happen in the CMOS circuit. One thing, the layout. We are going to change the layout, minimize the resistance by lots of VDD and VNN connections. We created a new M plus region, local region, on the way of current path here, so that it is going to minimize the resistance related to this input part and then this output part. Okay, and maximize P plus to P well spacing. You're going to make a part, so that you make the lateral bipolar transistor base width become large. If you make it large, then the beta is going to go down, and the criteria here, this is going to go down. Then you can make this thing bigger than this. Okay, so the latch up is not going to happen. So you change the layout to make a lot of low resistance regions on the way, so that to minimize the resistance on the part on this two end parts, and maximize the spacing of the base in the lateral transistor so that you minimize the beta of lateral transistors. VDD contact backside so that you can minimize the RP. That is the one thing you can do. And another thing is you do the channel stops ion implantation. Surround the active device with a doped surface region. This will reduce the RP and RN obviously, and increase the PMP, a vertical base width. This method will sacrifice the density, but commonly used for a long time to prevent the field inversion. But it is not common practice these days because the density is more crucial. So we have to do something else. Pseudo collectors, you set a extra collector here on the vertical bipolar transistors, okay, and then this you can set the extra collector here, and then this extra collector will reduce the RN. This method is useful for input protection circuit. Since P plus ring can collect injected hole, it can prevent the hole collection by P well. This hole collected by the P well is going to be the current and the lateral bipolar transistors. And on the way, you just put the pseudo collector, which is going to take all the holes before it reaches to the collector on the lateral transistors. That is one way to prevent the latch up, of course. And increase the emitter resistance. If you increase the REP here, then if you return to the criterion, if you increase the RP, then if you increase the RP, then this one, let me see. This is the RP. Let's make it a little bit big here. Okay. So we do not want to make a lateral bipolar transistors gain. It's bigger than this value. And one way to make that is we want to make this one big, okay, to prevent the latch up. So you can see to make this thing big, as far as the RP is concerned, RP should be big or small. If RP is big and this number, let me see how it goes. RP should be small, isn't it? RP should be small to make this whole thing big. And if the thing is big, then this latch-up criterion is not going to be met. Okay, let's go back. What it says on here, RP. Increase in emitter resistance. Here it says increase in emitter resistance. This emitter resistance is not an RP. This is a REP. Okay? RP is the resistance Can you see that? The RP is the resistance RP is the resistance of the N-type substrate. Okay? The REN is the resistance of the emitter here. Actually, which is the P plus implantation, P plus resistance. So that is a different different thing, right? So here, in this section says, we want to increase the REP, the emitter resistance. In other words, we want to reduce the source and drain resistance of the PMOS structures. And this is the figure showing that the latch-up beta product means the if you have a big beta, then you're going to have a latch-up. Okay, this is the emitter resistance. This is REP. So if you increase the resistance, then the criteria for the latch-up to occur is going to be bigger and bigger. So it is beneficial to prevent the latch-up to have high resistance of the emitter. Okay? And lastly, there is a lifetime control there. If you decrease the lifetime of the carriers in the bipolar, it's a common sense that the beta is going to be reduced if you decrease the lifetime of the minority carriers in the bipolar transistors. And you can see there are many ways to kill the lifetime of the minority carriers in the bipolar transistor to reduce the beta. And that beta is on the criteria, so it is obvious that, let me write down the criteria thing so that just to make it clear. Okay. Let me write down here. Beta NPN, that is the vertical bipolar transistors gain are beta P and P and 0.7 RP. That is the resistance of the P valve, IDD minus 0.7 by RP and 0.7 RN, and beta P and P plus 1 over beta P and P. Okay, that is the criterion. And then the things that we have discussed, the lifetime control is that we want to reduce the beta values by decreasing the lifetime of the minority carriers, and we want to decrease this beta so that this part can easily be greater than the beta NPN. That's what we are going to do. So that's why we want to kill the lifetime, and then the way to reduce the lifetime is the damage is obviously going to reduce the lifetime of the minority carriers, because this damages can work as a trap center recombination center. So damage will be caused by neutron irradiation, gold, platinum, which is just the inert element, doping to deep level trap, which reduces lifetime of minority carriers. Therefore, this will reduce the beta, of course. Both betas in lateral and vertical transistors. Reduction of PMP beta is more severe by reducing the lifetime because it is a lateral device. Therefore, beta becomes more and more transport limited, which causes increase in leakage current. Now, we have two bipolar transistors. And you have to think this part, that one of the bipolar transistors has a large beta inherently than the other one. This one has a wide base, so that it has naturally it has a low beta, and this vertical one has a narrow base width, so it does have high beta. So if you want to reduce the beta value, you have to work on this instead of this, because this one is from the beginning it has a low beta values. So if you want to reduce the lifetime, and then you're going to work on this lateral transistors better than this vertical transistor, because the damages is going to happen on this N substrate. Okay? So make a damage on the substrate is going to reduce the beta in this lateral transistors more than the gain of this vertical transistors, right? So, but we have a high leakage current because of the damages of this whole device. That is a sacrifice. Okay, so ledger can be prevented by reducing the beta in this lateral device, but we are going to have a high leakage current because of the damages of the substrate. And the lateral bipolar transistors inherently has a low value of beta than that of vertical transistors. So the lifetime control to decrease the latch up by damaging the silicon wafer is not a good way to prevent the latch up. Okay? It cannot be a good way, but that's one way we can think. And lastly, we can think of epitextual buried layers, and the configuration is going to look like this. All right. This is we are going to do the extra P layers on the well. Okay. Basically, what we are going to do is we're going to do the same thing for the bipolar transistors. We grow the epitextual layer on the N substrate, okay? And this epitextual layer is about 10 micron or so in thickness. And this epitextual layer was going to have the N-type because of the out diffusion, okay? And then we had to do for the P implantation on this to have a well, and then that the P is going to punch through this and substrate to make this configuration. And if you do that, if properly doped substrate is used, 10 to 17 and 18th, with P buried layer as shown above, both the resistance Rp, Rn will be reduced because of this high doped level. This is not a high, but relatively this P has been extended to N region. So that is going to reduce the beta value. Therefore, this method is very effective to reduce the layer chop. But this is a very troublesome. You have to do the epitaxial growth of the new layers, 10 micron, and that is not easy. You know, in bipolar transistors, this idea comes from the bipolar transistors making. And in the bipolar transistors, what you do is you have, say, P-type substrate, okay, and then you are going to implant the N plus layer and then do the epitaxy. You use antimony typically for the N layer, and then you grow the epitaxy layers on top of this, and then that's going to be P minus, and then you're going to have buried layers. Say this is N plus buried layer. We call this buried layer. Okay? And then you're going to build the transistors on top of this, like you have a ion implantation isolation, and then you have a P minus and N minus, sorry, this is going to be N minus and P minus, and then you have N plus emitters, like this. That is the typical example of bipolar transistors. Okay. And this buried layer part is going to be applied on this CMOS process to make this buried layer, and that buried layer is going to reduce these two values, the resistance, and then that reduction is going to affect the beta value of lateral transistors, so that the whole thing is going to be helpful to prevent or minimize the layer chop process in the CMOS. But as a whole, okay, we have to do something about this. We cannot use just the CMOS structures. But we cannot entirely prevent the layer chop process. We can minimize the layer chop in this way. CMOS layout and fabrication technology of a small device is not so clear as those of NMOS. Okay, NMOS case, you just following the scaling law, but in a CMOS case, we have to think of this layer chop process as well. So it becomes complicated. Okay, development of optimum structure has to be continuously pursued because we have many advantages of a CMOS over NMOS. So even though it has to be complicated, we should develop some process for the miniaturization of a CMOS structure, along with prevention of the layer chop process. Okay, next time we're going to move to the chapter 6, the electrical properties of bipolar transistors from Monday. Okay? Okay, I'll see you on Monday then.